So today, indeed, I'm going to try to talk a little bit about the special field of architecture and engineering, because indeed I have a double degree myself. I'm a civil engineer and an architect. And the specificity of architecture is, it's not really well known, especially in France, I have to admit, in terms of academic research. And I will not completely go into it, a single research that has been going on, but I like to show a little bit the field of possibilities and what could be interesting in finding links, because you were talking before, there's many different fields that the University of Cergy is covering. So there's enormously a lot of disciplines. And typically speaking, as I see it in other universities where I teach, architects and engineers, especially these hybrids, they go from the one field completely to the next one. We have a new master in our university in London, which is biological architectural design. But at the same time, we're doing fashion design, we're going to arts, we do humanistic, with the humanistic sciences. We do a lot of research. So I think it's an enormous wide field. And I would like to show you just a little bit, just to be able to discuss about it and give you a glimpse of what is going on. So I'm just going to talk first a little bit about myself, which might seem strange, but it might give you an impression of how come that the things are so different. Because there's already a first difference between architectural practice and architectural teaching and a lot of the other academic fields. I hope this functions. So this is me in my office. So as you said before, I have to correct one thing. Indeed, I'm the head of a structural engineering company, and we are worldwide. I will talk about it a little bit further. These are some of the things I do. And I have three fields that I cover mainly. So academic, BG, is my company, Bollinger+Grohmann. I've seen my colleague, Klaus Bollinger, the founder of our company, is online. That's very nice of him. And then the research also. So this is my parcours. This is where I come from. I'm Belgian, by the way. So I do speak a bit of English and French. That's nice, I hope. But today is only in English. And I also studied in Madrid. I work already since 20 years. I might be that kind of strange person that works for 20 years at the same company, from my first internship to now, where I'm also partially head of the global company. And you see in my timeline, these are some of the projects I've worked on the last 20 years, but I've continuously almost been teaching also, which is something. So I'm not a pure academic, definitely not, but I've always been teaching next to my direct practice. So I'm calculating stuff, I'm doing projects, I'm setting up new companies, I'm traveling a lot abroad for these projects because we work worldwide. But in the meantime, I was teaching in Ghent University. I've been teaching since 2011 in Versailles. I'm a senior lecturer in the Bartlett UCL. And the Bartlett UCL is quite important to me at the moment because we've set up 4 years ago, a triple degree of civil engineering, environmental engineering, and architecture. So the students come out of that studies with 3 degrees. And with CY, we're trying to do something similar at the moment. So I'm very happy that we can do that. We're very ambitious. It's not always going to be easy, but I think we're trying to work on these hybrids of the future also. So this is a little bit my context too. So that's our company. This was a workshop we held in Antwerp in one of our recently delivered projects. So Bollinger+Grohmann, we're now 450 people, I think, worldwide. We have 17 different offices. So that's a little bit of my background and my DNA too. The teaching, well, I teach structural engineering mostly. I also teach partially urban planning, digital urban planning. You will just find yesterday we put our latest podcast on Spotify to talk about urban planning, digital urban planning in different fields. So I'm already covering by that a wide range of things. And I also drop into this weird special things each time. And I'm trying to use all of them at the same time. So first of all, I'm going to talk a little bit about the architectural research. And before I talk about research on sich, I think it's important to tell where does that come from, because typically speaking, where I was a bit surprised when I got into the architectural teaching in France, I'm part of the research lab at the École d'Architecture de Versailles, which is called LEAV. And a lot of the research in architecture in France has been on history, the history of materials, but also just regularly the history of buildings. So there's a lot of links between philosophers, historians, and architects, typically in the research labs in architecture. Whereas myself coming from the north, usually we also have a lot of links with engineering departments, because architects, they want to build, basically. And since architects usually have this kind of weird idea, sometimes it becomes research an sich, because nobody really can understand it, but it works. And then it all of a sudden becomes research in an engineering department. And this is typically where I would say this double degree, at least in Belgium, where we have this, has always been the kind of field where you have this hybrid subjects or topics that are the part of the research. So through my teaching, I find out that I've always, because I'm teaching structural engineering to architectural students mostly, and I've always held very high respect to build one-to-one and to do prototyping. You will see also in my professional practice, I've been very lucky and that we have been working on extremely complex and new projects that have not been realized before. And in the teaching, I see a little bit of a similar axis, that the things that we are working on with the students, they are much prototyping, things that not necessarily exist. And especially the one-to-one. You see here the Solar Decathlon in Washington. It's a competition, it's an American competition that is also worldwide now, where students actually really build a pavilion from A to Z. And they have to make a self-sufficing building that is monitored over a period of time. Many different, they're a little bit small. I will get to a bigger projects. And why am I showing this? So there's, I'm sorry, I'm gonna have to. It's because it's this kind of pavilions. So you see one on the left side, for example, that's with my students in London. And I was teaching a class of patisserie to my students. So I do some strange stuff too. I thought patisserie might be nice because we use more or less the same utensils that you would use in architecture, and the way you would be talking about making a recipe would be similar, or searching for expansion would be similar to architectural fields. And in the end, some of the students came up with building a pavilion in sugar that they were baking for several weeks. It's a little bit like Hansel and Gretel, that they would make this tiles. And it was quite beautiful because it was a lot of different colors. And with the moisture in the air, they had a white napkin on the floor, and the drops, the sugar would melt slowly away, and all the colors would mix on the ground. And from this, you can imagine that actually certain things start to arise where you mix different fields, that you start to think about other problems or elements that you might want to face. This is one where with my colleagues from Vienna, we always do a big workshop in Versailles. I have 160 students in the third year. We do a 2-week workshops on something experimental. So it's called digital fabrication, the workshop. And this time around, it was on concrete canvas, which is a product used for making canals. So it's a kind of carpet filled with cement. And if you get it in touch with water, it gets rigid. And our colleagues in Vienna with some architects there did some research in previous years on this to make volumes and pavilions out of it. So I thought, why not do it with my students in Versailles? And in 2 weeks, we made these kind of pavilions. So we did some form finding. So it's all digitally calculated. So we have our proper tools that we teach to the students too. And then they built it. I have to admit, it was a bit of a sweatshop for the students because it's really concrete and it's not, maybe not so ecological. But the nice thing is that we use this also. So students were working on it. We do prototyping. We do things that we haven't done before. So we're finding out stuff ourselves. And we use it as a kind of research in progress. So we have been able afterwards to find new things about this. And this is typical. So this is another workshop with my students from last year. So we built bridges in 5mm thick plywood, and they were looking for foldables, folded structures. So there's a whole field of research also on folded structures. This is again this solar Decathlon. So I just show you some examples, and this is with an artist, Thomas Saraceno. I will get back to it later. But we built a pavilion which was 13 by 13 by 8 meters, also with students in temperatures of -5, which was not so nice. But and this artist was also at the same time exhibited at the Palais de Tokyo. And you see from this art, I will show you later how it became a real topic of research. We're now building, with my professional practice, I'm also building a pavilion which will be delivered in 2 months in Barcelona. So I'm happy to invite you. You will see it in the Torre Akbar. So I cannot publish images, but if you're there, this is the artist, because this is typically what then happens, of course. This is what I wanted to do with students as a prototyping process. But then since I need to work it out with my students, I first do it in my office. So this is the patio in my office in Paris. And so we worked on different parametric approaches, calculation methods that we had to adjust to try to find several stuff. So this artist works, he has the biggest collection of spider webs in the world. So mostly spider specialists drop new spiders at his place so that they can build spider webs. And they get scanned by the Max Planck Institute in Germany. And they get a lot of, because there's a whole series of researches of how, there's about 30 different ways of building spider webs. So it depends on which sort. So there's probably 8,000 different sorts of spiders, but there's only so many ways of how they build the webs. And so from there you can actually, so they are scanned to the millimeter. And this artist has the biggest collection of them. So they work pretty much together. And to help build up his pavilions, we came up with genetic algorithms as an approach to find, and we're trying to attach AI to his, to help him develop his artistic inventions. So that was the artist. This was a pavilion we built. And this is what I think is interesting from an architectural school. You might expect that we do historic research, but by the way that they are doing experimental stuff, you can actually really find new elements to explore and research. And I think that already comes into the studios. This was another project I did with my students. That this was unfortunately during lockdown. So I thought, let's let them play a bit digital. And I know here with Cergy, we have some contact on 3D printing also. So we already did some projects. We tried to do some projects together. And here, through my contact with Sika, this big company from Switzerland, I told them, listen, there's a lockdown. So can you help us? Maybe we can teach the students some new methods. And finally, Sika printed for free and delivered for free 30 different columns that the students designed during lockdown. So I think this is, it's not particularly research, but you know, it's a new material. The students get to work with it. And by the way, they are exploring new forms. Often for Sika too, it was, I don't know how to do this. So I need to update my machine. Maybe I need to invent a new machine. Maybe I need to do this. And by going much further than what a regular engineer might have thought in the beginning, actually the architects put them against the wall, like, okay, you have to find something new. And I think this is typically very interesting, also, especially with students, how to get there. There's some of these things, like the experiential teaching that I'm practicing. There's already a lot of research, and especially nowadays with lockdown, we're not sure what the best method would be to teach to students. Some of the universities in France took it up, and we have been funded by the state to do this research, and it's called experiential learning methods. And so together with Amaco is a specialist in earth constructions, and they put up a team of 7 universities in architecture. to try to come up with a new way of teaching also. So it's partially MOOCs, it's partially with exercises that go real scale. And this is also to show that even in architectural universities, we're not only about history, we're also a lot about material, new learning methods. And I think there's a lot to cover in different universities together. So in order to test it, of course, what you do in an architectural university is that we then propose a workshop to students. So we worked with the Compagnon de France, which, to be honest, the French always underestimate themselves a bit. And they have the best masonry guys in the world. So to work on massive stone, there's actually only the French that really know how to do it. I'm exaggerating, of course, but and I'm not only with the French public, so I have to be careful here, I guess. But anyway, even where I'm working now on some projects with massive stone in the UK and in America, I have to admit it's French people who do it in the end. So the persons that are really getting out of the stone the right product, it's French masonry persons that are formed in this kind of schools, the Compagnon de France. And so here the Compagnon de France, together with 20 students from Versailles, we said we need to try if this method of teaching works, like experiential teaching. So there's an exercise. We also had the MOOCs. And so we went making a bridge based on a design by Leonardo da Vinci from the 1500s for bridging the Bosphorus. He made a 300-meter bridge design, which was never realized. Otherwise, we would have known probably. And we built it in small, only 7 meters. So it's not really the same, right? But we built it in 1 week with the students. We had, I think, 80 or 90 stones to cut out by hand. And this was fantastic because all of a sudden you had the Compagnon de Devoir standing at the same block, or the students of the Compagnon, together with architectural students coming from very different backgrounds, talking about how to cut this stone. The one came from the military and he wanted to redo studies. So as a Compagnon, the other one was an architectural student. And I think this is also building. If we do buildings in the end, you bring a lot of different topics together. You know, if you have a house around you, it's not only just a pure architectural design, it's a lot of techniques, it's a lot of data also that you can gather around you. It's about moisture in the air, it's about comfort. And I think all these fields, an architect and engineer have to cover somehow. And I think this is, the university is an ideal place, or architectural universities are ideal places to test it with students. So this was done in a week, very nice. We also taught them some graphic methods to work it out. And this is only to show that from there's possible links with other fields, right? And the output, what is very nice for me also to see in this context, mostly to this workshops, we attach also some colloquiums or international symposiums where we invite people from all over the world. And this, again, this comes, of course, because I work in the private sector also. So I meet a lot of people from different countries already like that. So I can freely invite these people. And I also do a lot of free speech, free lectures in other parts of the world. This is a little bit what we said to ourselves, that if we can give this back to the academic community, this we should always put on the first plan also. And this means, like, for one workshop here, we had all these speakers. Of course, now with Zoom, you can invite everybody from all over the world. But even on a regular basis, so on the left upper side, you have somebody from Shanghai. On the lower side, you have 2 people from the UK, then somebody from Barcelona, from Denmark. They all have their own research labs. So most of them are practitioners, especially Philippe Yuan. He's the most crazy person I've seen, I think. You really look him up. He has, I think, an office, a professional office of 100 people. He has a factory where there's 20 robots constructing things in timber, but also printing 3D. He has a research lab of 50 researchers, and he's a professor at Cergy University. So I think I think always that I have a lot of energy, but he's better. And then we also these symposiums where we had 400 people in Versailles. We have a very nice, I mean, here there's a nice environment, but in Versailles, we have a little chateau also. And our school is just in front of the chateau. So if you're ever there, just please drop by. It's fantastic. If you want to do nice lectures, we can do it. But we had a lot of these people, and this is also the output with my students, right? These are some papers that we wrote also with the students about this concrete canvas. So it was at the IASS, a very important congress for engineers. And this is written together with my students. And I think this brings them also the first step to do research later. And this is something which is much more used in other countries. When I see it in the UK or in Switzerland or in Belgium for that matter, I think there's more research done by students that become a researcher after their studies than you have here in architectural universities. But slowly, since the architectural universities in France have a different status now, I have the impression that we can get there too. So this was to show you that it's possible with architects to do some research, and it can come from very different corners or very different projects. Another thing, and this is to make the link to Cergy also, I think we still see it later too, but there was an appel d'offres, so there was a candidature to be handed in. It's the doctorat par le projet. I don't remember the title in English. It's, I should look it up, but it's something that comes from the Anglo-Saxon world. I know it pretty much from Australia, basically, where people, it's much more practice-based research and practice-based doctoral thesis, which is something relatively new. The French state is investing a lot in this. And I think Cergy is one of the first universities, I believe, in France to really put a lot of effort in it also. And I thought this is a unique chance to get our universities together also. So the lab of Versailles, together with the lab of Cergy, we tried to hand in a project which was too much for the architecture university because it was too much of structural engineering, but which fit exactly into this kind of research and doctoral thesis. So the doctorat par le projet. And at this point, I will get back to it later, but I think it's an ideal chance for architectural universities to get closer to the more, at least in France, it's a real chance to get different fields together into one doctoral thesis. So if you ever have a topic that could span different universities, because in the end, this is for me also what it's about in academic research. It's looking for hybridization, the serendipity, looking at different fields where actually things touch each other. Because if we only, of course, you can typically in structural engineering, the research could be that 100,000 times you break the same stone and you will get some theory about it, but it doesn't really help you to build a building afterwards. So this is also the second aspect to it. An architect will always have in mind to build a project with it afterwards, of course. So it's going to be much closer to research and development than the pure fundamental research. I think in pure academic worlds, this might always be a little bit a tricky shot, I think. For me, coming from combining the professional world and the academic world, it's typically within the things that I'm doing. It goes much faster in the private sector. We can test a lot. I can test a lot with students, and typically architects always think about realization and not this fundamental research. But there's so many loose ends in there, and I think it's pretty much interesting. So this one, the one that we chose to submit for the candidature, and where, so Madam Sandy Kate Fenton put up the title. So it's Design of Lightweight Structures, and it's the potential of machine learning methods to reduce the impact on climate change. So you see there's a huge variety of topics in there. It's the future of architecture. We need to be much lower on carbon footprint. So that's the first one. So it's ecologics. You need to talk about all this with different material science people. It's about machine learning. Machine learning, typically speaking, the architectural world is always the latest to learn something. If you think about structural glazing and gluing of parts, it exists since the 50s, and it's only the last 10 or 15 years that we actually really do it in buildings. But that's because every building that we do is singular. It's not an industrial standard, so we cannot just repeat things. So it makes it quite complex also to find things that would come back. But it has the advantage that it's a big field. Once you find something, you can apply it to a very big field, of course. Lightweight structures, again, also something typically of the engineering field. So it brings already together the material science, structural engineering, and computation, which are three very distinct worlds an sich, but it makes a lot of sense to bring them together. And for this one, well, we also work with workshops. So I'm supervising this doctoral thesis. I'm also, I explain it later, but it's a thèse chiffre, which is the French way of public-private sponsored doctoral research. It means that you get partially paid by the state, but partially it's by a private company supporting the research of a doctoral student. And so this is the first time we try it, but this is also very, I have to admit, in Germany, the conditions for doing this are much less favorable. And even in Belgium, I cannot do it on the same way. The French state is actually is giving a lot of help to this. And I have to admit, it's the first experience we do that as a private company. And I think it would be nice in the future to do more of them. We typically test also, again, this topic with workshops. I will go fastly through it. So this was the first part. This is a little bit what comes from an architectural university, I would say, and my work at a research lab and what would come out of it, the typical output. And then at Bollinger+Grohmann, so as you said before, it's that's the professional company where I work. Just this is where our offices are. I mean, it's pretty much in Europe. You find out it's very centered. Well, we opened Shanghai, but we cannot put anyone there, but because we cannot travel there, so that's a pity. But okay, we're trying. No. This is typically what we do as projects. So we work worldwide on a wide range of different projects. It's going from the biggest cantilever in the world to the entry of the MoMA in New York, or the Hermès shop in Beverly Hills, for that matter. And so we're combining a couple of fields, so structural engineering, facade engineering. And we have something where our colleagues, at least in our Vienna company, they were always very much at the forefront in developing tools and complex geometry, because we always worked on very complex geometric projects. We developed our own tools, and this is also why we have a little bit of a standing in the development of computational tools. So I will go further into it a bit further. And at some point I asked to my colleagues, so what do you think about what would be the words that describe best our practice? So this comes from a workshop. So I used the words that they brought up, but then I put my own images in the background. So maybe it's not fair towards them, but I just took over the words, right? So this, I will not go deeper into it, but this is typically some of the projects, and you might understand from seeing the complexity of these projects that we have the advantage also to test a lot of new stuff. So this, for example, typically a cantilever in plexiglass, and all the bolts are also in plexiglass. And this has not been done before. And typically we like to do things that we actually don't know how to do either. So that's a nice part of my job, I would say. If you go to Lausanne, please do visit this one. We're also doing the building next to it. It's a big shell structure in concrete. And the biggest span is 85 meters. It's by the architect Sana. And as I showed you before with this artist, Thomas Saraceno, we've been working a lot with him. He was already a student of my colleague, Klaus Bollinger. He has an artist practice with around 60 people in his office. And this was a project for Sydney spanning 140 meters, and people would be able to walk into these clouds. So you can imagine that's not the most easy part to do. These are typically, I see it. The projects where we're working on, this is Saclay. Maybe I should not have shown it actually, but it's another university here in Paris. Sorry. Cultural projects, a lot with artists. And I think it's very nice because usually I don't have to prove too much. In France for the insurance, you have a proofing engineer. But mostly for these artist works, and especially in foreign countries, I don't have to prove anything. I'm the only one who's signing off on it. So I can do pretty much what I want. And it's true, I take a lot of risk then, but it's also the nice and fun part. This one is unfortunately still not opened after 1 year that it's finished. It's from Zaha Hadid, but with the COVID, they wanted to have a nice concert, but it's still not opened. Dominique Perrault. And this I will get back later to it. This is also things that we are working on. And of course, even we're 3D printing houses, and I will get back to it later also. So what I want to try to show you is a bit that also in my professional practice, a lot of the projects already are research an sich. And I will show you how as a professional practice, we deal with this kind of things. So one of the biggest ones where we have been working on a lot is the development of tools. And in this case, it's a structural design tool that is a parametric structural design tool, which is called Caramba, and which is can be plugged into off-the-shelf programs such as Rhino. And I don't know if you're familiar with this, but these are programs that are typically used by architects. And our first book that Mr. Klaus Bollinger did together with Manfred Grohmann was called Workflow. And see, this is one specific aspect of our field. We have to work with a multitude of people to achieve a project. Typically, for the Louvre in Lens, for example, I worked for 7 years on that project. So it's a long time. And from all the stakeholders, you start from the competition. It was actually 8 years with the competition. From the start, you have a lot of different people with specialties. You have the people on the construction side, you have the client, you have all these stakeholders into one project. And we have always been very close to the architects, and to translate what the architect is wanting to do, it's not always the easiest task. And we've seen CAD helping the design in the last 20 years. So from the 90s, I would say, people got rid of their drawing tables and started drawing into 3D. And from that point on, we've thought, this is probably an opportunity also. For a lot, it was a lot of hassle because it was a new tool. But we thought maybe this can help also to bridge the gap in certain discussions. So if the architect, we can implement into his CAD approach, also the structural approach, so that the discussions we have, so the workflow would improve, because typically you would get a model from an architect, you would have to somehow translate it, so discretize it, put it into another machine or another software, then into another again. And from that one, once you have a result, you say, this is the problem. And then the architect acts again. So you can imagine the loop that you have to do each time is enormous, and you lose a lot of time, specifically in the concept finding, where the impact is still the biggest of the people working together. And this was typically why some of my colleagues developed this parametric structural design approach. And so the program is online. You can actually buy it. I think for students, it's for free. We also have one which goes on top of that, which is doing genetic algorithms and optimization with genetic algorithms. And this is a field, well, we've developed the program 15 years ago now. And I think now more and more people are using it. But typically speaking, we use this already since 15 years to do architecture. And so the other program is called Octopus. You see it here. And it's a multi-criteria optimization program, which would use, so it's the Pareto optimum between several solutions. And you see here an example. So if you look at that roof, you have several ways of proposing this roof. So an architect would typically say, I want this to be higher, I want more daylight here, I want this and this. So a parametric approach. I would say I want this and this as a structural parameter. You throw the parameters into the program, and the program automatically would generate, let's say, a first 100 children. From those first 100 children, he will try to analyze them and say how they are performing. It's not very nice of us, but okay. So we do tell them you get, and normally this used to be a single criteria where you could do it. And with Octopus, we can do it multi-criteria. We can do up to 1,000 different criteria upon which we analyze and give credits to one single solution. So from the first 100 kids, we use their DNA and we recross them. And actually in the genetic optimization, we have to be careful that we also keep the bad students, because otherwise we don't have a wide enough variety. The pool of variety is not big enough. You would imagine a whole island with blonde boys with blue eyes. It's actually against one disease it wouldn't work, for example, no? So there you need to keep the pool of variety wide enough. And this is typically where then all of a sudden you create 1 million variants, for example, and where you see, okay, I take the 5% best performing against different criteria, and then you let decide the architect. Or they add another parameter, or we add another parameter. And this is typically where the workflow comes in much more handy, and we use this tool also to then fabricate mostly the things. It goes very far, I would say. And again, what you will see in my professional practice, since we have these tools and we play around with it, we love to play it. Huh? So I have to admit, there's a kind of inherent thing. We like to go to our office and we like to do things where just for fun. So we also offer workshops. And so this was one here that we did in Paris with the reuse of certain elements, but also this is a workshop I did in Hong Kong some 10 years ago, where we thought we would make a deployable structure and then let it float in the air. So we bought a lot of helium to let it float, but the helium proved too expensive, to be honest. So we couldn't let it float. So we used it to make the funny voices in the end. But it uses a very complex algorithm also to find the position of the points where to place them. But also here in Tongji last year, where we did another workshop. So we do this next to it. And then I told you before about this because, and actually I should have put the other chapter before. At the moment, especially in France, and Europe is much more following, since a couple of years, the European Union has put a lot of effort in helping smaller private companies to apply for research and development funds, which is called in France the CIR, and which to be honest, I never knew about it. It's only since a couple of years I know it. And in regular times, you will not believe it, but 80% of that funding in France went to the banks, because banks invent products that they actually say this is going to be ecological building. So they're funding a new portfolio and the state is helping them to set up this program. It makes sense in a certain way. But typically speaking, for smaller companies like us doing this kind of software development, I mean, until 5 years ago in Paris, we were 20 people. And typically speaking, in a normal year, 20% of our hours are into competitions or into these special projects where we actually don't win money. We do workshops and all this. So, and since a couple of years, we can benefit from it in France. And I notice even in Germany, Denmark, Switzerland, Austria, Italy, we can actually pretty much and more easily than ways before apply to this kind of funding. And I think it has greatly enhanced also the way that we do it. We can take it one step further, basically, because the general research and development we were doing, we can take it one step further. And one of the steps further, because we were already trying with these spider webs to use AI, or at least machine learning, not AI, I would call it. It's because that's really another step. And that's where we called, we see there's a CIFRE. So it's a private, public funded research. It's over 3 years, and this is typically our students. And again, this is a fantastic collaboration. No? We have the lab because then again, it's interesting. I have a private company. I want to work on one topic that we've been doing since 20 years in our company. I noticed there's some funding there, but then I'm a teacher in Versailles where I see, okay, Versailles can benefit of this. We're working together with Cergy to put up this double degree program. I am from Belgium, so I know very well, and I run the office also in Brussels. So I'm very close with the University of Brussels, with whom we do write a lot of articles. And for the student, it brings a lot of benefits, of course. So there's a kind of networking, but in the same time, all the labs are also benefiting from this. I think it's quite, I mean, we're trying it and we'll see what gets out of it, but I hope we can do a lot more of these things. So again, what is interesting for me with our private company is that we have a lot of network. We have now, I told you, we have 450 people, and we have a lot of people that are professors also in different universities all over Europe. And we are asked a lot to be in juries in different universities, in ETH or in Tongji. And here my colleague is a professor and the dean in Berlin at the Architectural University. And they are doing a lot of research on new acoustical floors for offices, but also 3D printed at the same time. So this is, I'm not going to go too much in detail, but you see typically again, this is part of the research of the things that we know how to do it in our private company, but it goes back to the Architectural University to become a doctoral thesis or a postdoc research, basically. I'm going to fly through it. If I go, we can still discuss about it, of course. There's a lot of these things. And I know I go a bit fast on this, but why I wanted to talk about it. So my colleague was doing this, and at the same time, we had a request here in France to work on this 3D printed houses, where we were working with one company and we tested some things, of course, and doing new modeling, because now we developed for one of these companies also a new modeling where actually every single string of this 3D printed elements goes automatically in the parametric approach. So they film it, they take the temperature, they see how fast it's drying up. And these mechanical characteristics go into a calculation model, basically. So this is then what we could, again, do from the private side. But it goes through projects in a certain way. So this was, unfortunately, the project that we did here didn't get built and somebody else did this one. I'm not going to comment on it because it's a bit... And then that company came back because they had a problem with water tightness of the building. So we did some new testing. And this kind of knowledge, what we also try to do as a private company, we try to work open source. So our software, both of them that we use for the calculations are open source. So everybody can play around with it. And actually with most of the knowledge that we build up on these things, unless the clients write that we have an NDA, of course, but mostly we try to open it up into conferences. We try to show it around so that other people can go further, because we only can benefit from knowledge if we really share it, I think. And if we want to be better for the future, that's the only possible way, in my opinion. But there's not so much about concurrence. There's much to tell about. We're all colleagues in the battle to become better, I guess. So, and it then goes on, and this was then with this 3D printing, the knowledge we built up in that we built up in Berlin, we used it to do this competition for a bridge, which we didn't win, but we did it together with Cergy University, then here with the research lab. We used again some new tools that we developed from the software. I still hope we can build it. So I have now maybe a client that wants to build this thing. So I'm still trying to find ways how to really build it. And this is then, at the moment, we're also looking a lot at topological optimization. So it's a lot of mathematics. So we want to try to go further in there too. And our software already does it a bit. And again, this one is actually the last one that was really built. And it's, if you go to Berlin, it's in a shopping mall, you will see it. You can, well, it's the dressing rooms basically. So you have 5 of these. We wanted to print them initially in earth, but it became concrete in the end. So But each time we find new things, and I think that's the ideal, of course, from the professional practice going back to the university, using the partners that we have in the private field also into the university and vice versa. And I think it's a very happy marriage until now. So that became then the columns. So this one is standing around at the university. So 2 words about this research tax credit for those that are not French. So basically you have to explain what you do as R&D, and you have the Frascati guidelines in Europe. I don't know if you're familiar with it. So it's fairly open. It has 7 criteria against which you can judge if something is research and development. It has to be, of course, published. So that's one of the things. And again, that seems quite logic. It has to be new, of course. But it's quite open. And we found with some, when we were looking at our projects, somebody else, we did an assessment. And indeed, a lot of our projects actually got elected and selected for this R&D funding. And these are some examples. I will go very fast through it. I don't want to go too much in detail. I'm trying to, I know I have too many slides. I'm sorry for that. And about each of these things, these are long-term projects also, mostly like the one here for Hermès Rive Gauche. I worked for 3 years on it, and there was no company doing the things I wanted to do. So we invented a new way of unrolling the slats of the timber. And we took onto our own hand the G-coding for the machines that were done in the factory also. So these are typically things where we then get again very close to the industry. But this kind of very complex, highly complex timber, because timber is a fantastic product because it's already digitized since 50 years actually. So you can really go very far. And architects do tend to forget that our professions are getting more and more digitized, that you can use the robots, and that it's not against the low-tech approach or the handcraft approach in a certain way of what we had in mind. But all carpenters are using tools to work on timber. And this complexity of timber and finding new ways of making forms, making shapes, analyzing it, gluing it, we have been looking at it the last 20 years. And so these projects, I've done 4 or 5 because initially we wanted to do it with steam bending, and we did test in our patio in the office also to do steam bending, but it proved too long, and MS was even open to the question to build a factory for that, but it would have taken too long to build Hermès Rive Gauche, so we couldn't do it. So we found another way, and then we did some stairs in Moscow and in. Then another one, I don't remember, but the last one we did in 2015. So this was ongoing since 2008 that we were looking for the right method. We built projects in the meantime. But then in Sydney in 2015, we finally built a stair that was built with steam bending with some boat builders that built over 2 floors, this whole thing. And these are some of the images. I can do a full lecture on this alone, actually. But and again, the same approach on timber and our knowledge on new manufacturing. We put it to fruition for another project. It's 400 square meters. It's fairly small. The building costs only 400,000 euros. It's an exhibition hall. It's in Belgium, somewhere in the middle of nowhere. And we use an ancient technique, and this is also specific to timber. We try to reinterpret ancient techniques. So you first already have to build up the history about it, the history of making, the history of, here we wanted to have massive timber, so no gluing. And it's called reciprocal frame. And we put it to a complexity that nobody ever did before. So we used our tools again, our genetic algorithm tools and optimization tools, to find new ways of making this kind of project. So I will flip through quite fast. But again, to find this way, it also went together with the workflow with the architects because they were looking for a grillage that was continuous. First, they wanted to have concrete, but I told them that's not very ecological and it's going to be too complex, it's going to be too heavy. So we said massive timber is the way. And here we had 5,000 different beams that were all cut differently, each one of them, but it's all digital. So it doesn't really matter because it goes through the robot. It's just 2 cuts each time. But that can be connected with 2 bolts only each time. And it's all massive timber, and they could be carried by a single person at each single point. That was our idea. And it's like a grillage. It works like a shell. So in the end, I think we had 650,000 variants that we tested, which is a lot. And the architect could choose. So this is what we came up with then. So the construction. And of course, then again, we brought it to a conference, the IASS. It's a conference that is only talking about shell shapes and this kind of history to the future, manufacturing to history, how you improve the future by the history is of course a huge field of interest to engineers and architects alike. Now, this is the last chapter. I think I'm already quite late. No, it's okay. It's okay. Okay. I just asked my colleague also put me together some of the things that we got granting for the CIR, for the research and development for our company. And you will see some of them actually go together. That we tested it with students, we tested it in the office, we make a real building, we do again a test with students, we do some publishing, we meet some new people, we do another project with it, and all of a sudden it becomes, okay, we can really do something with it. And then it can go into research, maybe like now the machine learning. I have to admit, it's a very new field for us, but we have 4 people in our company that are really very good at it and that are optimizing carbon footprint programs with it. So I think I'm very hopeful that it can work for us. Not the typical machine learning that you do with images, because for us, that's not enough data. But typically engineering and architectural products are all singular. So how to find the common element in all these projects. And this is it's a huge field of research actually. So this was indeed the spiders, which I told you. So there's all the books and the knowledge you have from the Max Planck Institute, where we try to find out, okay, can we learn our computer to braid webs like a spider? So we would train an agent that would become the spider in the web, which is very hard. I mean, you have to imagine these spiders, they sometimes jump meters to go to start the next wire. So it's very complex. And of course, we only did this to help the discussion with this artist, because cable structures are enormously complex, especially if you have a lot of them. To have a state of equilibrium, statically speaking, is very, very complex. So if you want to do genetic algorithm on it, it usually doesn't work because the calculations are much too complex. So it takes too much time. So our frustration was that with the artist, he came up with an idea. We started to model it. We started to learn from it. It took us quite some time. He did it in a physical model. He scanned it. So we take it back to a 3D. We start to learn. We optimize a bit, we send it back, and he says, but I already have a different model. So, and you're almost not learning from it. We said like, we have to find a way that we can actually suggest him really new solutions that go into his artistic mind also. So why not become the spider? And the idea is to train the agent towards what he's wanting to do. We're still thinking about it. So we're learning by doing, but that was the initial idea. He can learn from the artist, he can learn from history books. So like, let's analyze all the possible ways of building a spider web, from structural analysis, from certain parameters that you could put in. So this would be typically the machine learning. And to be honest, we got in certain ways closer, but not close enough. We now find a better way also of calculating webs, but typically that's a doctoral student that finished his PhD that developed a new way of calculating these webs with mathematical formula, which goes much faster. So he's one of the specialists now to do this. And you see it, it's a kind of, it's actually not the right comparison, to be honest, but We called it the matrix of the matrix because you have to build up functions, but actually it's even a bit different because you would be the smaller one, and this one has to run through everything and he has to redo it and he has to learn everything. It's a start. At the moment we built one project with the artist, so you'll see it in Barcelona. And we will have to take next steps. And the other person that is doing machine learning is on this carbon footprint. And I think we can then start again with putting the data in. But it's going to be slow and long. Another typical process, maybe some of you work with this, but imaging is one of the biggest things probably for the future, right? I mean, you see it at the Meta base. They have the HoloLens, the other one, the AR glasses. In imaging for biology, it's already there so far with it, and it's all based on the chaos theory. Also, like how do you see the volumetrics? In architecture, we're so slow with it, though we work with images so much. And it's only the last couple of years that we try to use these things. And there's a big field. And again, in our frustration, we were working with an artist. So there's some research going on. People construct through these with the AR glasses on that you build towards the 3D model that you actually have in front of your eyes, which could be one. You can also now go on the construction site with these and compare the models with what you've designed, with what is really on site. But what we were trying to do is actually that you would design, this is a truss that we're designing, and we have our own calculation tools. So the person can actually design a bridge just by drawing it by hand. And this came also out of a frustration with the work of an artist, where the bigger his sculptures got, he cannot really do it in a small modeling anymore. And then he had somebody to translate it into 3D, and then it became something else. And so you have so many steps. So at the moment we're trying that we develop a tool for him so that he can design directly his sculptures in 3D, that it's working structurally also. So it's a bit this, because these sculptures go together with bricks actually. So the surface is discretized with bricks. There's several ways, and we have to do some mathematics also that it works actually still. So we're busy with doing that. But typically this is an enormous field of development. And we found out now that our tools are way too slow. So we need to go into the computer gaming technology. So you have to need, if anyone knows Unity quite well, I'm happy to hear it, because we as structural engineers, we don't know how to do it. And it's really, to go much faster for us, it's really interesting. So I hope, so this is the artist actually. So he's working on these sculptures, and typically to help him, we're trying to set up that he could design it directly into 3D. Another one also coming, and this is typically how you do research now. You have a problem, and that's where you want to look for a solution for. So the first thing in a research is, what is the problem? And here the problem was that with bamboo, it's very frustrating to work with bamboo. Already in Europe, actually, we don't have bamboo. That's the first thing, of course. So if it's delivered, you don't know the quality. So the rules go, and the new norms also go, that you have to double up more or less with security factors. You have to double the amount of bamboo that you would actually need. And the experimental approach of security factors is not really well developed. And there's a second thing in bamboo, is the joints are always very much of, it's quite miserable, because it costs enormously a lot of money, because most of them are done in steel, and you have to do them to size. They're not just, nobody's wanting to do it just with ropes anymore. So we tried to come up with a new solution, and it comes also from the work we had on an art piece in Arles with an artist from Asia. And so we tested some of these things here in Cergy already. I also did some tests in the VUB in Brussels. I worked with the Navier lab, and typically in my office, we have a lot of students that do their final diploma, final degree in engineering. And so the last 6 months they work at our company, and we let them work in the labs of the universities, of course. And so this is very interesting for the students. We also do architectural projects with it. We did tests with it. And now I'm looking to set up a postdoc program with the UCL in London, for example. So this was the art piece where we had a lot of frustration. We did some testing, but it's, you can see it's really, I wouldn't call it scientific testing, but it works, let's say. And then again, this is compressed earth. We tried to set up a program together with the University of Picardy, because in the north, there's, not beyond the wall, but in the north, just in general, they have a lot of funding for digital approaches and new materials. So we're trying to build, actually, it's this little house. We're building it with earth compressed tiles that are made from the earth on site. So, and then this one, this is with my colleague. And again, this is a lot about imaging. They image the space entirely around you, and they build now sensorial spaces where you would immediately perceive the design that you've done. So acoustically, the moisture, everything. So you would, it's called design with all senses. It's together with a lot of architects and engineers. This is the University of, the Technical University of Berlin. So the space is entirely modeled. If you change the light, so everybody as a designer, without that you go on construction site, you would experience the whole space. So, and it covers all different fields. It's acoustics, it's about comfort, all these things. I think it's quite interesting. It's and this one, I will skip it, but this was a very big, this was fundamental research. It's glass filled with water. We just we brought out the product 2 years ago, but nobody wants to build it. So it's fundamental research, I would call it. But it's with the flow of water in the, it's to optimize, I will just show the test case here, how the hot water goes up actually. By the hot water, then you have an electrical wiring that makes sure that this water can go up again. And it reduces the heat coming in and also the cold going out. So it's okay, but it's a lot of effort to fill 2 glasses with water. And it has new gluing techniques also that you need. So this is why it was interesting for us also. And this is the one in Barcelona, but I will not show it. Not show it, sorry. No, it's this one actually. So this was quite complex. It's 12,000 different cables with 12,000 different joints, and that all with all different pre-stresses that are installed at the moment. And you have no reference point in space to really install it. So it's a bit complicated, but they're almost there. They're almost there. So this is the production. And then again, on the tools, we work a lot on this kind. These are buildings that we do, of course. Oh, what is this? Accès non trouvé. Okay. Yeah, that's not. But these are typically projects that we develop with it, and then we use it. Oh, this is the same, I think. So what's next? I think this is what I wanted to say today. I think there's a huge interest for me to see architects going into very, very different and wide variety of fields, that they discover things, and it's extremely interesting to pick up some of the things that they are working with. And I believe schools are a fantastic lab in a big way. The students are experiencing a lot of new stuff. You can work a lot on very special cases with them. And I think what is very specific for the academic field, and I know this is not typical, but working in the private sector, in the public sector, in different universities, I think it makes a huge benefit, at least for me and for some of the things that we're working with. I can test things in reality with my company that I could not do in university, and vice versa, basically. So that's a little bit what typically for architecture universities, this exists. Most of them are practitioners, which is not the case in regular universities normally. And then there are some things around in the private sector. There's a lot of companies trying to do research also like we are, and I think it's very nice at the moment. So research and development, design and realization, and thank you very much.
Thank you very, very much, Klaus, for this amazing lecture. I hope that everybody can join as I did.